Okay, so we received another question about how one would go about determining the direction of the stack growth. In other words, does the stack grow up or down, or are the stack addresses ascending or descending? So that's I would say a fairly common kind of general question. I don't necessarily see it being asked often in, let's say, a very senior sort of engineering position, but it's kind of like a general purpose sort of question. I think this one is reasonably common. Does anyone want to, before I start sharing my thoughts for how I would do it, anyone else here want to share some of your thoughts for how you might go about determining via code, like writing code, how would you solve this question?
Possible to just keep track of the addresses, a few set of addresses as we keep calling functions. And then we know that then we compare those addresses that are saved in the array to see if they're increasing or decreasing.
Yeah, I like that. Before I dive into that further, any other thoughts? Any other alternative ideas?
Just declare two local variables. I mean, you can compare the address of two local variables. That should tell you.
Oops, wrong color. Yeah. So let me just kind of outline what you're saying here. So let's say we're in main. Let's say. And it doesn't really matter what, declare an X, have a Y, and then you would do something like if address of Y is greater than address of X.
Yes.
Is that what you were getting at?
Yes.
Cool.
Yes.
Oh, perfect. That's fantastic. And actually, I'm not sure offhand if. Yeah, I thought I want to share on this, but I'll get to that in just a second. But yes, this could be an approach that you could take to check whether or not the stack is growing upward or going downward, and you'd see whether or not the second variable has a higher or lower address than the first one. Are there any? If you have any concerns with this approach?
Oh, Glenn, I have concern with this approach. How do we make sure that we force the compiler to create X first and then Y next? Excellent
point. And this actually ends up being essentially the same problem as what Manish had suggested earlier. Manish essentially suggested, like, okay, let's have some other function foo, and then as input to foo, let's take a function pointer, not a function pointer, an integer pointer, and then within foo define int a, and then say if address of a is greater than I. I think that, hopefully I'm not stepping out of bounds, Manish. I think you're saying something on those lines, and then over here within main you would call foo with address of x, with the hope that when you call another function, the stack pointer would be increased, all that kind of normal stuff that you'd expect would occur, and then we can compare the address of a local variable allocated at this main function compared to the address of a local variable allocated in this other function. So both of these problems kind of have, as was just very astutely pointed out, have the same problem, as they rely on the compiler to do what we're hoping for them to do. We're hoping that if we write here to instantiate a variable y, and if we write that after this line, we're hoping the compiler creates the appropriate code to do things in that order. But I think as we've learned in at least in the foundation video, and we talked about briefly on Sunday as well, is that especially once you start enabling compiler optimizations, that ends up being an unreasonable assumption to be making. And the same exact problem happens here with calling this foo function. it's possible that the compiler decides to inline that function and place it here. And then there's a second kind of round of optimization, then places this instantiation or allocation of A back up here at the top of main. So between inlining and reordering, this might not give us an accurate answer.
But what if we do y is equal to x? Then we would force the compiler to create x first and then do y. Does that work?
So maybe I should understand this. So, and I realize I have a lot of squiggles going on, but over here you're saying something like set this equal to x. Is that right?
Yeah.
And you're right. This might potentially, well, this would, at least in theory, stop the compiler from reordering these two variables. See, these two lines alone isn't enough necessarily, but in theory, we could make it a little bit more complicated, such that the compiler would no longer reorder them. But there's still no guarantee that the compiler isn't going to optimize in some other form such that these end up being in a different order than we expect. In other words, if we never end up using X again after this, maybe it just ends up being a register. And maybe there's not necessarily a guarantee that just because you declare a variable in your function, that there's going to be memory associated with it. The compiler might just say, you know what, I'm just going to use a register to store this data because I don't need, because I have enough registers and because I'm not doing enough other things with the registers, I might just be able to get away without allocating memory at all.
I have an idea, Glenn. So
sure,
we can use, so we have this foo, like, and then we have a variable, local variable in there, and then from the main, in the main we declare another variable which we can pass to this foo function and use these two to compare. So that way we know that there won't be any inlining or other optimizations, and we can use that address to compare.
So I missed that first part. How is what you were saying different from the foo example here?
So I'm we are comparing against this main, the variable created in the main versus the local function.
Mm-hmm.
So wouldn't that still? So generally that would probably give us the, should be able to give us the direction to go through.
So to be honest, I'm not entirely following what you're saying, but I think you're kind of on a good track of like, is there something that can we take this foo example and change something such that we force the compiler to always actually call another function? And well, the answer is, generally speaking, yes, there are things that we can do to force the compiler to always have a function called foo, thus that, in other words, not inline it. And let me go with two different examples. One example would simply be to turn off optimizations. We can simply say, what is the code to turn off optimizations? It might just be this, but there's probably something else. I don't remember offhand, but we can turn off optimizations as part of our compilation to force this ordering or to force this foo function to continue to exist. So that's one approach. If this question was asked in an interview, sometimes this is a reasonable answer. Sometimes the interviewer is going to want you to think a bit further to see what else can be done. Another way we could go about forcing this to, especially in the case of this foo function, forcing this function to still exist, is place this foo, or place the implementation of foo in a second object, because the C compiler, the C compiler isn't smart enough or isn't capable of inlining functions that are in other objects. So if we place foo in one object, 1.0, and then we have the main in another object, the compiler won't be able to inline foo. And therefore, if we call foo, we for sure will be actually calling another function and could potentially do something like this. And I'm sure there's other ideas that maybe folks here have, or we could certainly hypothesize other things that we could do that kind of take advantage of, let's call it compilation or linking options to kind of enforce this sort of behavior. But I want to point out one more thing, which it's kind of a cop-out answer. But in both of these examples, we were talking about comparing these pointers or comparing the addresses of these two objects or comparing these two objects. But comparing pointers is technically undefined behavior in the C spec. So if we want to really get like persnickety about it, we can't actually do this universally safely. In practice, this probably works fine almost every time. But from a C spec perspective, this actually isn't something that we're allowed to do. Comparing these pointer addresses and trying to infer something from that. So kind of a cop-out answer, but that is potentially another answer to this sort of question. And I think that's something that's worth keeping in mind for other questions as well, is interviewers sometimes are, I don't want to make it sound like interviewers are trying to be mean, but sometimes they'll ask you a totally reasonable question that if you really thought about the question, it doesn't actually make sense, or it isn't actually possible to do it. And that is a totally valid response to the interviewer with regards to that question.
Raghu here.
Yes, Manish, we have a question?
Let Raghu go first, sorry.
Yeah.
Okay, sorry, Raghu.
Yeah, so Glenn, when I think about it, there are two aspects to it. First of all, we need to force something on the stack, right? So it could be a function call, it could be a software interrupt or any kind of interrupt which will actually force the control to use the stack. That is one part. The second is having the variable also on the stack. So instead of the register. So if you have a local array, then we will get contiguous memory, which are assured of order on the stack. So you can compare, or you can do arithmetic on the offsets and then see if their addresses are incrementing or decrementing.
No, excellent point. To actually enforce or to ensure that we don't end up getting optimized into a register using an array. Yeah, fantastic suggestion.
And also it is contiguous in memory. So two successive, or if the offsets are positive, then you should have incrementing addresses or decrementing depending on the direction of the road. So it assures contiguity of memory and order.
Yeah, fantastic. Excellent suggestion. Manish, did you have a comment as well?
Actually, I was thinking that you already, if you could get the stack pointer register variable in assembly, you can just track that.
If you could get the stack pointer and track the stack pointer, yeah, that, and we'll talk about inline as well. I guess for those who haven't gone through the modules yet, we'll talk about inline assembly next Sunday, and so we could potentially use some inline assembly to retrieve the stack pointer, or an intrinsic potentially to retrieve the stack pointer, and then use one of these other techniques that we've talked about to check the stack pointer at 2 points in time where we know that we would have expected the stack to have grown, and to see which direction it grew. Excellent idea. Any other thoughts, comments, or questions about this?
So if we just define an array and like compare the first address and last address, would it still work?
If we allocate an array and compare the first address, or the 0th entry in the array and the last, or the 10th entry in the array,
Yeah.
and check whether or not the addresses increase or decrease.
Right.
Raghu, I correct me if I'm wrong, but I'm not sure that that actually guarantees kind of from a universal perspective.
Yeah, I guess, I mean, that's true. I mean, the array allocation on stack, whether it's going upward or downwards, would still be an incremental addresses, right? So that's what the compiler take care of it. So I don't think that approach would work, comparing the first address and some later address and making comparison based on that.
Is it because like the contiguous allocation can be in either direction? Or?
That
right,
is
right.
my
It depends on what the base address you are picking, right, for the array. So if you are picking up the base address such a way that you have the stack space after that, doesn't matter the stack is going up or down, or you have enough space allocated in the stack, and you pick the base address, which is generally a lower address, and then the next indexes will be at higher addresses. That's how I think at least compiler does it, and that's how you could do, even if you do a pointer manipulation increment, it will go to the next address for the next element, right? So, I mean, that's my understanding. I
that would be that would be my expectation as well. But I want to give Raghu, I think he was saying something along these lines. I want to make sure I'm not missing a case that I'm not thinking of at the moment.
Sorry, Glenn, I'm not following the explanation of Subhash. So my understanding is that we are talking about a local array inside the function foo. So we are not talking about a global array, and therefore it will be on the stack. The question is, will it be, will the base address be arbitrary? It can be, I mean, I have not seen the compiler decide, okay, it's possible that the compiler takes a further address and then starts the, pins the 0th element there and then goes in the other direction. I have not seen it, but I'm not sure about that. If that is what is meant, that it is not guaranteed. I would think that it is going to be in the natural order of the stack growth, that as the offsets increase, it will grow the stack.
And maybe I think there might be a couple of different questions going on here. I think I'm starting to get myself confused between the several different questions that have been going on. So Raghu, just to clarify what you were just saying, I think the expectation that Subhash, I believe, mentioned earlier was that if you're allocated an array of 10 entries of who knows what, the address of the 10th entry will always have an address greater than the address of the lowest entry, the first entry, regardless of which direction the stack is growing, simply because of the nature of, if you want to get the address, if you want to, for example, dereference an array, you can dereference the array and get the 5th entry, like getting the address of the first, and adding size of times 5 times the entry, the array size, or the array of any particular entry in the array.
Okay, so that's applicable for arrays on the stack as well.
I would think so, and then that's why I was curious if there's exceptions to this. One thing, the thing I did still like about using an array is, we talked before how something could be optimized into a register, but if you have, well, A, enough different variables, or B, large variables, they won't be optimized. Well, presume you actually do something with them, they won't be optimized into a register. So that would be one way to guarantee that that particular address or the particular variable actually ends up being allocated. So once again, there were several problems that we were trying to solve. One was to make sure that things were being allocated in the order that we were interested in, and the other was to make sure that they actually were being allocated.
Glenn, is it possible that the stack frame grows in different direction and the variables placed in that stack frame could be in opposite direction?
Sorry, if the stack grows in one direction and variables placed in the other direction?
If inside a stack frame, the variables are placed from top to down, but the stack frames in the stack are placed from top bottom to top.
This is, I think, kind of what I was getting to earlier as well, which is what we're talking about essentially is not something that is defined by the C spec. What we're talking about is what, in most cases, the compiler has decided it wants to do. In some cases, maybe the architecture has some play in it as well. but it's simply a, I don't want to say an arbitrary convention, but there's nothing stopping someone from doing it implementing this in a completely different way, such as increasing the stack pointer to make enough space for all of the variables that need to be allocated for that function, and then placing the variables in, who knows, some sort of random order within that allocated stack space. In fact, one could even say that a compiler might want to reorder things on the stack in order to have better alignment and utilization of that memory. So I don't, obviously now we're getting back into the compiler optimization question. But the point I'm trying to make is that we're talking about a convention that isn't universally true. But when someone asks this question, if you get asked this question, they're not necessarily trying to trick you. They probably actually think that there's a real code that you could write that will give them the answer. So you can point out how it's not possible to do it because of X, Y, or Z reason. There's a lot of reasons why this might not be possible or doable depending on the constraints they give you. But if they ask this question, they probably actually want to see some code to do it. And you can make some reasonable assumptions about how the system works and how the compiler works in order to write code that's going to do this. And I think we talked about it a little bit on Sunday as well, about in the context of instructions and how some instructions are faster or slower than others. And on different architectures, there might be different costs to accessing memory as opposed to just using things within registers. And you can make all sorts of arguments how there is such an architecture where memory loads and stores aren't any more expensive than any other processor instruction. Like that architecture could exist, but that would be, in my mind, more of an exceptional case rather than the typical case. So when you're trying to answer these questions, it's best to think about, okay, what does kind of the generic typical system look like? And let me give an answer that works for that system. If you want to look smart and give some kind of other fancy answers, totally fair game. But be prepared to still give a kind of general purpose. Someone gives you an arbitrary generic processor and compiler, what would that likely do? And then go from there. Sorry, that was my soapbox speech, if you will.